Hello and welcome to Chandler Science AP Physics 1 Kinematics and Graphing Motion video. In today's lesson we're going to kind of wrap up the kinematic stuff, put the final piece of that puzzle in there, and then we're going to look at how to graph motion and different types of graphs and how to kind of translate graphs back and forth from one kind of graph to the other and so on. So without further ado, let's get started. Don't forget, if you're in my class, you're taking notes and you're going to write down 3 questions at least over today's video. And if you're from anywhere else on the internet, welcome and I hope you enjoy. Let's get started. Alright guys, so a quick recap of some kinematics terms. Velocity and acceleration, very important. We already discussed position. We already discussed velocity too, but just a quick recap. So velocity is v. It is defined as a change in position, x, over the change in time. Its units are meters per second, and it's basically how fast you're going in and what direction you're going, right? Now, we're going to start off talk about one-dimensional motion and two-dimensional motion today. If you're talking about one-dimensional motion, you can only go one of two directions, positive or negative. So remember that negative sign doesn't mean it's like a small number. It means that it's just going in the negative direction. All right. Now, acceleration is, call it a, and it is defined as a change in velocity over the change in time. So it's very similar to same kind of formula, right? But it's the change in velocity instead of the change in position. The units for this are meters per second squared. Sometimes you'll see this written this way, meters per second per second. Now, the reason why I write it that way is because that's what it is. It's the change. It's meters per second every second. So in other words, draw a little motion diagram to kind of illustrate this. So let's say you start off with your velocity is 0 and you're at an acceleration of, let's say, 2 meters per second squared. What that means is that 1 second later, right, your velocity will be 2. And 1 second later after that, your velocity will be 4. And then 1 second later, your velocity will be 6. Now notice how the motion diagram, the gaps between each dot is getting bigger because I'm accelerating, I'm speeding up. And my velocity is changing from 0 to 2 to 4 to 6, but my acceleration never changed. It was always 2. Okay, a lot of times students get confused and they think, oh, I'm speeding up, so my acceleration is increasing. No, your acceleration is constant. Your velocity is increasing, right? Because that's what acceleration is, a change in your velocity. In AP Physics 1, we're going to have 2 kinds of acceleration. Constant acceleration, so it's going to be a set number that doesn't change, like 2 or 4 or -5 or whatever, or you'll have 0 acceleration, which means your velocity is not changing. You have what's called constant velocity. But we're not going to have a situation where the acceleration is changing within the context of a problem. All right. So with that being said, we got velocity, acceleration. I hope you understand these terms and what they mean. And we've already discussed them in class a little bit. So let's move on and talk about the rest of the kinematics equations. You do need to know these 2 equations right here. These are important, and they're not on the formula sheet. What formula sheet? This formula sheet. This is your formula sheet for that you're going to get on all the quizzes and tests in class and on the AP exam. And so I want to focus on the first 3 equations right here. These 3 guys right there. Now these equations are important. Okay, they're called the kinematics equations. I want to talk about them just for a second here. My color back to white. All right, so we've already derived this first, or rather this second one. We derived part of it. We derived this part of it in class, x equals x naught plus v naught t. We did that in class. Now, the rest of this I want to talk about real quick. Anytime we have a problem where we have some an object or a person going in, running down the street, or some kind of, we'll do some problems in a second. I want to be clear that you see this little x here on like this x right there, and then right there, and then x there, and then x there, and there, and then there, and there. Okay. A lot of times students get confused with what those x's mean. I want to clear that up right now. Those x's refer to the plane you are in, right? Now when I say plane, here's what I mean. We got the one-dimensional kind of x-plane this way, right? Then we have the y-plane, which goes up and down. And then we have the z-plane, which goes in and out. Now we don't do 3-dimensional stuff in this class. We only do 2 dimensions. Okay, so the x is there. It doesn't mean that you can only use those equations in the x kind of plane. It just means that if you're going to use the equation, you have to make sure that your velocity vector, let me get my pen back to the red, your velocity component here, this guy, needs to be in the same plane as your acceleration, right? In other words, you couldn't do a problem where you had the velocity this way and you plug it into that formula, and you had your acceleration, but your acceleration was like in the vertical plane. You couldn't kind of combine those 2 numbers. It doesn't work. They need to be in the same plane. So they put an x on there to kind of remind you, hey, make sure your velocity and acceleration are in the same plane, not same direction, but same plane, going this way or that way, right? But not one up and then one this way. Like, that won't work, right? I hope that makes sense. If not, ask me in class or shoot me an email. All right. So yeah, so those are the 3 equations we're going to be using. We've already derived one of them mostly. We'll kind of finish deriving the rest of that, the 1/2 AT squared part. We'll derive that later next week. So now we have these equations. You can jot them down real quick. You know, like I said, you always have this formula sheet in class, but go ahead and jot them down if you want to, and let's do some problems using these equations. All right. All right, so let's do some problems now. We have the first one here. You accelerate your car from rest at a rate of 3 meters per second squared. If your final velocity was 21 meters per second, how far did you travel? All right, so remember the guess method. I want to use that during class. Remember the guess was for the givens, the U is unknown, E is equation, substitute, and solve. We're not actually guessing, right? So what do we know? What does the problem give us? All right, well, let's see. Right here we got a number. Usually the numbers are usually going to be given. So we accelerate from rest. Ooh, that is an important term there. From rest means from stationary position, right? In other words, what was our initial velocity, v naught? 0. That's a given to us at a rate of 3. What's the rate of 3? Or accelerate, right, at a rate of 3. So our acceleration is a positive 3 meters per second squared. Your final velocity was 21. Oh, so we have final velocity is 21 meters per second. So that's our givens. What are we looking for? Oh, here we go. How far did you travel? All right, so we're looking for our change in position, or how far we went, or our displacement, right? So this is what we know, and this is what we're looking for. Now, what equation? Let's go back to our formula sheet here. What equation are we looking for? What's going to be the right one to use? Let's get rid of this out of the way. All right, what equation are we looking for? Well, what do we know here? What do we know? We know that we have final velocity. Let's highlight the ones we know. We know we have final velocity and initial velocity. We know those. We have the rate of acceleration. We have A. We have initial velocity. And we have A. Okay, now what are we looking for? We're looking for, I'll put in blue the thing we're looking for. Right now, the thing we're looking for has to be in the formula, right? If we know all the stuff, but the thing we're looking for isn't in the formula, well, then the formula's not going to do as much good, is it? So we're looking for the change of positions. So looking for that guy, and ooh, it's like delta x isn't even in the first one. So here we go. So which equation are we going to pick? I think we're going to pick this one. Now, why that one? You might be thinking, well, I don't like that one. It's got squared signs in it, 2 of them, and it looks ugly, and I don't like it. Well, that's fine, but look, do we have the t? We don't have t, do we? So the blue thing is what we're looking for. We don't know what the change in position is. So we need to find the change in position, delta x. But the second equation, we also don't know what t is. So we can't solve the equation if there's 2 things we don't know in the formula. Right? So the one I circled is the one we want, because we have everything else. We have A, we have the final and the initial, and we're going to solve with this delta x, right? The change in position. So that's the equation we're going to use. So let's go back to the other slide here, and let's put that one in. Let me go back to my right color. There we go. So we're going to use v squared equals v naught squared plus 2a times, and I'm just going to write delta x instead of x final minus x initial. It's the same thing, right? Change of position. And I'm going to rearrange this to get it to our delta x by itself before I plug in numbers, which is I want you to practice doing too. So I'm going to have v squared minus v naught squared over, oh sorry, not over, whoop, my bad. Let's do it this way, 2a times delta x. Now I'm going to divide by 2a. Getting ahead of myself, I don't want to go too fast. Those 2a's cancel, so now I have delta x was going to equal v squared minus v naught squared over 2a. And now I can plug in numbers. And where did my calculator? There it is, my calculator. I just moved recently, so all my stuff's kind of in different places. So let's plug in my numbers here. So my delta x is going to equal v squared. What was my final velocity? It's 21 squared minus 0 squared, that's easy, over 2 times my acceleration rate, which was 3. Alright, so what do we got here? Plug it in. Boop-a-doop-a-doo. 21 squared divided by 2 times 3, which is 6. And I'm getting 73.5 meters, and I think that seems right to me. And there we go, 73.5 meters. That's how far we went in the positive direction, right? Awesome. Okay, let's do one more. All right, so one more problem, and feel free to kind of stop the video and go on yourself and see if you can solve the problem on your own, and then check yourself with me afterwards, right? That's totally fine. I'd encourage you to do that. So, all right, here we go. This one, you are skiing over flat ground and slowing down at a rate of 2 meters per second squared. All right, so it says you come to a stop after 14 seconds. How fast were you going initially? All right, so what are we given? What do we know right off the bat? Let's see, we're slowing down at a rate of 2. All right, now we're slowing down. A is 2. Now, I'm going to put a negative sign here because we're slowing down. But I want to be clear. If you are slowing down, it doesn't necessarily mean your acceleration is negative. All right, well, I'm going to talk about that in a minute. But for now, I'm going to put a negative 2 in front of that. You come to a stop. Oh, you come to a stop. What does that mean? That means you stop, right? I mean, what's your final velocity? Sounds like a 0, right? I don't need units on 0, do I? All right, after 14 seconds. Oh, so we know it. We know delta t this time was it took us 14 seconds to come to stop. How fast were you going initially? Ooh, okay, so we're looking for v naught. We're looking for v naught. That's what we're looking for. That's our unknown. Go back to our formulas here. Let's pick the right equation we want. Let me erase this other stuff. All right, so okay, what do we know? We know this time. Go back to my highlighter. All right, what do we know? All right, we know time and we know acceleration. So this time we have the t. That's good. We have final velocity. Final velocity. We're looking for initial velocity. Ooh, we don't know how far we went though, do we? It didn't tell us how far we actually traveled. And we don't know initial velocity. All right, so we're looking. All right, and then what are we looking for? Put in blue. Looking for initial velocity. Initial velocity. Initial velocity. Okay, so the problem here looks like it's going to be that I don't know that guy and I don't know that guy, and I can't solve an equation if I don't know two things. So it looks like my winner is this guy because I know TA initial velocity. I'm sorry, final velocity. I'm looking for initial velocity. So I think that's my winner right there, that first one. So V equals V naught plus AT. All right, let's go back to our thing here. The right color again. Okay, so we're going to use V equals V naught plus a t. Well, I should say delta t, right? That's probably better. That's more correct. Delta t is technically correct, which is the best way to be correct, right? All right, so here we go. Now we're going to plug in our, not plug in numbers yet. Sorry, got ahead of myself. We're going to rearrange the equation for the thing I'm looking for before I do any of that. So it's pretty simple, really. It's just going to subtract this over to this side. So I'm going to have V minus a delta t equals v naught. So now we can plug in numbers. So v naught equals my final velocity, which was 0. Well, that's easy. Minus negative 2 times delta t, which was 14 seconds. And my initial velocity is going to be 0. And that's a plus, right? So it's going to be 28, plus 28. With a negative sign, turns out two negatives make a positive, right? It's 28 meters per second. And my final initial velocity must have been 28 meters per second. All right, there we go. Okay, so hopefully you got that. If you stopped the video and you went ahead and solved it, hopefully you got 28 meters per second. That's the correct answer. All right, now quickly about this whole positive acceleration, negative acceleration thing. Okay, guys, listen. This is important. If your velocity is positive, right, to the right, and you are slowing down, that means your acceleration must be negative, right? If your velocity is to the left, that means your velocity is negative, and you are slowing down, that means your acceleration is positive. In other words, if you are slowing down, that means that your velocity, the sign of your velocity, positive or negative, will always be opposite the acceleration, right? If you're slowing down, that's a rule, right? Remember that, don't forget it. If you are speeding up, that means that your velocity will be always the same as your acceleration, whether it's negative or positive, if you're speeding up. Remember, guys, a negative sign does not mean smaller or, or bad or whatever, okay? It just means direction, okay? Things can go in the negative direction all the time, probably about half as much time as they go in the positive direction, right? So I want you to remember this rule. Slowing down means acceleration and velocity are opposite directions. If you're speeding up, that means velocity and acceleration are in the same direction. Okay, it's important to remember that actually moving forward. So write that down. Okay, so I'm not going to do any more sample problems right now. We're going to move on to the graphs. All right. I'm actually going to wrap up the video for kinematics right now with example problems. I had made the graph video, but it got really long, so I'm going to cut off this video here. So hopefully you have 3 questions from this video. Remember, guys, if any other questions or concerns, you can always email me, shoot me a text on Remind, or any of that stuff. So I'm going to end this one here. And the next video I'll release will be over graphing, all on a standalone video by itself. All right. Thanks, guys. Thanks for watching, and I'll see you later.